Welcome to today's lesson. Today we're going to be talking about reciprocal functions.
Reciprocal functions. If f of x is our original function, then 1 over f of x is our reciprocal. There are 7 rules you have to learn about reciprocal functions. Let's learn them first and then take a look at what these reciprocal functions actually look like when we graph them. Rule number 1. Where the graph of y equals f of x lies above the x-axis, so does its reciprocal, y equals 1 over f of x. And where the graph of y equals f of x lies below the x-axis, so does y equals 1 over f of x. It's reciprocal. Our second rule for reciprocal functions is that where f of x equals 0, the reciprocal 1 over f of x is undefined. Well, where does f of x equal 0? That's where does y equal 0? When y is 0, we have x-intercepts. And what does undefined mean? It means we have an asymptote, a vertical asymptote. So for the original function where we have x-intercepts, on its reciprocal function, we're going to have vertical asymptotes. X-intercepts go to vertical asymptotes. Rule number 3 is, for f of x equals some a over 0, where a doesn't equal 0. In other words, where do we find that? Where 0 is in the denominator? That can't be. That's going to be our vertical asymptote. Well, its reciprocal would be 0 over a, which equals 0. What happens when f of x equals 0? We have x-intercepts. So vertical asymptotes for our original function become x-intercepts for our reciprocal function. Our fourth rule for reciprocal functions is that the graph of f of x and its reciprocal, 1 over f of x, intersect only along the lines y equals 1 and y equals negative 1. Y equals 1 is a horizontal line above our x-axis, and y equals negative 1 is a horizontal line below our x-axis. Why is this the case? Well, we're asking, when does f of x equal 1 over f of x? When are they intersecting? When are they equal? When y is 1, or when our output is 1, we get 1 equals 1 over 1. Yes, that works. And when our output is negative 1, negative 1 equals 1 over negative 1. That's the only time our functions, f of x and 1 over f of x, are going to be equal. Rule 5 for reciprocal functions. If the graph of y equals f of x has a horizontal asymptote at y equals a, then y equals 1 over f of x has a horizontal asymptote at y equals 1 over a. For example, y equals 4 is a horizontal asymptote in our original function, then y equals 1 over 4 will be the horizontal asymptote in our reciprocal function. Rule number 6 of reciprocal functions. As y equals f of x, our original function, increases, its reciprocal decreases. And also, as y equals f of x, our original function, decreases, its reciprocal, y equals 1 over f of x, increases. We can see here that as the absolute value of f of x goes to infinity, meaning it's either going to infinity or negative infinity, our reciprocal value goes to 0. If it's positive going to positive infinity, this will go to 0 from above. If this is going to negative infinity, this will go from 0 from below. Because remember, if this is positive, then this is positive. If this is negative, then this is negative. Similarly, if f of x is going to 0 from either above or below, because it's absolute value, then its reciprocal is either going to positive or negative infinity. The absolute value will go to infinity. So if this is going smaller and smaller and smaller to 1, 0.5, 0.25, 0.125, this is going to get bigger and bigger towards positive infinity. And if this is going negative 2, negative 1, negative 0.5, negative 0.25, negative 1.25, this will be going bigger and bigger towards negative infinity. And our seventh rule of reciprocal functions states that as f of x is going towards a max, its reciprocal is going towards a min. And if f of x is going towards a minimum value, then 1 over f of x, its reciprocal, is going towards a maximum value. Here we have an example. If f of x is our original function, which is x minus 2, x plus 1, first we can graph that. We know it's going to be a parabola because when we FOIL this out, we're going to get a trinomial with an x squared term. So we know it's quadratic. Our a term in ax squared plus bx plus c is positive, so it holds water, it opens up. And that's that black curve there. Well, if I want to graph its reciprocal, I have to put 1 over x minus 2, x plus 1. And that's going to be this red curve here and there. So let's look at some of the features that we learn in our 7 rules. Number 1, these two graphs meet on the lines y equals 1 and y equals negative 1. Here they are intersecting there and there along the line y equals 1, and there along the line y equals negative 1. The maximum point of our reciprocal function is corresponding to our minimum point of our original function. The original function has x-intercepts here and here. We know what the roots are. The roots go to 2 and negative 1. Those are our x-intercepts. Well, the roots become our vertical asymptotes, because if we restrict the domain, x cannot equal 2, or this goes to 0 in the denominator, and x cannot equal negative 1, or this goes to 0 in the denominator. That's why we have vertical asymptotes at negative 1 and 2. The roots became the vertical asymptotes. When f of x, the black, is increasing, here it's increasing, we see that the red, the reciprocal, is decreasing. But when black is positive, meaning it's above the x-axis, the red is also staying above the x-axis. Here we have a positive value for f of x, so our reciprocal remains positive. We have a horizontal asymptote at y equals 0, because here, as long as this is positive, this will stay positive as well. As you see, this is increasing towards infinity. Our red curve, which is the reciprocal, is decreasing to 0. Increasing to infinity, here we are decreasing to 0. Similarly, when our black curve, our original curve, is a negative value, our red curve will also be a negative value. As the black curve goes towards 0, then 1 over 0 goes towards infinity, in this case, negative infinity. As the black curve goes towards a value of 0, a y value of 0, then the reciprocal curve also goes towards infinity, in this case, negative infinity.